Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation for my YouTube channel. And this time, the title of my presentation is Strategic Technical Analytical Evaluation of the Implementation of a Major Overhaul, that is a major outage maintenance for a gas insulated switchgear, and that is applicable to 10 of these gas insulated switchgears, and that itself requires a lot of strategy, technicality, and analysis. My good name is John Kweku Amotu, and I've been a professional electrical engineer for quite close to 31 years, and I'm based in the United States of America. Next slide, let's talk about the outline of my presentation. And the first thing I'll talk about are the standards, the industry standards that govern a gas insulated switchgear. And what is a gas insulated switchgear, and when do we use them, or when do we apply them? We'll talk about the application of the gas insulated switchgears. Then we'll move on to the indoor and external installations. As you know, a gas insulated switchgear can be installed outdoor, or it can be installed indoor in an enclosure or in a building. Then we'll talk about the different manufacturers, industry players for the gas insulated switchgears, the voltage levels, and typical voltage levels is from 69 kV to 800 kV, and the types of GIS that we have. And this will basically take us to talk about the single phase and the three phase configurations of the different types of gas insulated switchgears that we have. Then we'll take a look at the different product lines from a typical OEM, from a typical manufacturer. Then we'll talk about the applications of the gas insulated switchgears. When do we implement it? Then a typical comparison of an air insulated switchgear, that is an AIS, and a gas insulated switchgear, and a lot of them has to do with the footprint, space, right, and the compatibility, and the reliability, and the reduction in maintenance cost. Right? GIS has the upper hand in terms of lower maintenance cost. It's typically, maintenance free, but then and then it all depends on the application and the environment that you install this GIS. So most manufacturers say that it's maintenance free, but after 10 to 15 years in operation, definitely you need to implement some maintenance to it. Then we'll talk about the typical bus arrangements that we have. We have a different bus arrangement: the single bus, the double bus with a double breaker, and a ring bus, and a break and half arrangements for the gas insulated switchgears. Then we'll talk about the external connections to the gas insulated switchgears, and we have connection to an SF6 bus, and also typical connections to an air insulated substation. And basically, a typical connection to an air insulated substation, we use typical air to SF6 bushings. That is exchange of an interface of air to SF6, and that is integrated to an air substation. For an oil to SF6, basically these typical connections are to the high side of a power transformer, so that basically inside the transformer we have oil as the insulating medium, and on the side of the SF6 gas bus enclosures is SF6 as the insulation medium. So that is why we have oil to SF6 as an interchange point of connections between the power transformer and the GIS switchgear. Then we'll talk about the components of the gas insulated switchgear. The SF6 The gas insulated switchgear has different components, and we'll basically delve into all these different components. And just to make a mention of it, we have the circuit breakers, we have the disconnect switches, then we can have earth disconnect switches or fast earth disconnect switches. Then we have the instrument transformers, that is the current transformers and the voltage transformers. Then we have the feeder cables. Then sometimes we can have surge arresters that is internal to the GIS, and also an external surge arresters if there is an interface between an overhead line and a cable. Then we'll talk about the strategy that was implemented to review the need for performing a major overhaul for this gas insulated switchgear. And the first item that we'll talk about is discussion of the major overhaul. What all is about. And what was the timeline. The time-based maintenance that was implemented for the overhaul to be performed on the gas insulated switchgear. Next, I'll talk about the actions that I took and the analysis that was performed and my recommendations. Then the last but not the least, basically other technologies out there. As you know that, as part of the reduction in global warming that is basically being enforced, being followed by many utilities out there and other industry players, right? They are all pushing for an alternative gas, SF6 free. So they are utilizing carbon dioxide and nitrogen oxide and fluoronitride components basically as insulating medium in these latest technologies of gas insulated switchgears. Now let's talk about the standards that govern a gas insulated switchgear. For every analysis that you perform and every governing maintenance that you want to implement, you need to basically talk about basically take a look at the governing standards, right? Okay, so for a gas insulated switchgear, we have IEEE standard C37122, and this is just a standard for a high voltage GIS substation in general. That is a gas insulated switchgear that is located in a substation, right? And that is for voltages of 52 kV and C37 122-1 is specifically for GIS switchgear that is rated at 52 kV and above. And the C37 122-2 is for 52 kV and below. Okay. Then C37 123 is how to specify what are all the things that you need to specify for a high voltage GIS that is greater than 52 kV. Then last but not the least is the IEC comparable standards that also is a guide for high voltage switchgear and the controls for 52 kV and above. Next slide. Now let's take a look at why do we need a gas insulated switchgear. There are a myriad of reasons that needs to be understood by any discipline engineering to understand the need for implementing and for applying a gas insulated switchgear. Okay, so the first item that we need to talk about is basically it is very ideal and basically best if you need a substation that is in a congested city, right? Okay, so if you have a congested city and has a high amount of population, and basically it is quite close to the load, then that is when you basically have to think about a gas insulated switchgear because of the enormous attributes that the gas insulated switchgear has. Secondly, it is very compact, right? And as you know, for these congested cities, right, and highly populated cities, right, space is a premium, right? And basically you have tighter spaces, So basically, it becomes applicable to think about implementing a gas insulated switchgear. Most often than not, the OEM, the manufacturers of these gas insulated switchgear will basically delineate or indicate that a GIS is maintenance free, but it's quite close. I'll say much more of a quasi truth. But on the other hand, you also have to think about it being in operation for about 15 more than 15 years. Then you have to think about also implementing some maintenance in it to ensure the reliability for the basically extend, enhance the life cycle of the GIS. Next is talk about the reduced installation time, right? Okay, so this basically comes into play during construction, right? Okay, so during construction, you are doing your best to basically reduce uh, construction time, right? To meet due dates, right? And also to be able to complete the projects on time. So the way the gas insulated switchgears are basically come in modules, right? Basically, and already assembled in the factory, basically makes installation time much faster. So basically, you are able to achieve a reduced installation time. Next, reduce cost of maintenance, right? Okay, so as you know that basically it is in a metal enclosed switchgear, right? Okay, everything is in basically compacted, right? And basically, the OEMs will tell you that it is maintenance free, right? So I will tell you that most often than not, the first 10 years, you basically, will not have any problem. 10 to 12 years, you don't have any problem with a GIS. Maybe, you can experience a little bit of SFSS gas leak. Even then, that can be fixed quickly. So it basically results in reduced cost of maintenance. Next is a reduced footprint. Yes, sir. Because of the compact nature, right? As you compare a gas insulated switchgear footprint, right? The size, the dimensions, right? Compared to an air insulated switchgear, right? An air insulated switchgear for the same capacity has a higher dimensions compared to a GIS. Next is a gas insulated switchgear is very ideal for an environment that has a high amount of pollution, right? If you look at a lot of these industrial facilities, right, okay, that has a high oil contaminants, sand contaminants, dust contaminants, and also if you have a facility that is close to the shore, right, you have a salt elements that is basically, intruding into this switch here. So because it is enclosed in a metal enclosure, all the components are enclosed, it basically becomes the ideal candidate for a highly polluted environment. Next is a reduced project risk, and basically, I made mention that basically due rates, installation time is reduced, right? As such, basically it reduces the risk that is associated with projects, and a lot of the risk that is associated with projects are basically delays in meeting due dates, closeout dates, right? Okay, because they come already assembled in the factory, it makes installation time much faster. Next piece is basically the safety part, the safety piece, right? Okay, because all the internal components are in a metal enclosure, the high voltage components are not basically accessible, right? It and not exposed, right? Okay, so on the safety part, or on the safety piece, right, or on the safety front, basically it offers much a lot safety to um, personnel or operations and maintenance personnel that will be in close proximity to these GIs. Next is approved, right? Okay, so basically, any arcing, internal arcing is extinguished much faster because of the way it is compact and in a metal enclosure. There's also viewports, right? Okay, so that allows you to basically be able to identify the position of the switches, right? We have disconnect switches, we have circuit breakers, right? So these viewing ports allows you to basically see the position of these switches, whether it is in an open position or closed position. Next, lockout tagout, right? Okay, so if there's a chance that basically you need to perform maintenance on it, or let's say if there is any problem with it and basically you need to perform isolation of the GIS. Basically, there are dedicated lockout tagout provisions that are provided by the OEM for you to basically be able to isolate these GIS components. Next slide. Okay, like I made mention in the earlier slide, right? Okay, a gas insulated switchgear can be installed indoor, right, and outdoor, right? Okay, so for the indoor installation, as you can see over here, these are typical installations, right? Okay, so these installations are ideal for highly contaminated environment where you have a lot of dust, right? A lot of sand, a lot of salt contaminants, oil contaminants, right? Okay, so then that is when it becomes very applicable to install a GIS inside an enclosure. Okay, so and also if you have the gas insulated switchgear to be located quite close to the shore, right? Okay, so or basically if the water table around the vicinity is very high, then that is when basically you have to elevate the enclosure. So as you can see over here, the enclosure of the GIS is much elevated, right? Okay, so this is also a typical example of an indoor installation for a GIS. Next, we'll talk about the industry players, right? The industry manufacturers, right? That manufacture a gas insulated switchgear and the typical voltage levels that they manufacture. And also, we'll talk about the types of GIS that we have over there. Okay, so as you can see over here, the first one is Hitachi ABB, and General Electric, Hyundai, then Alstom, Siemens, and Schneider. Okay, so these are the industry players out there that basically build up robust and very good products for gas insulated switchgear, right? Okay, so for voltage levels, okay, as of now, we have from 72 kV up to 800 kV, okay, because below 72 kV, right, it is not ideal, it is not economical to, in terms of cost benefit, to utilize SF6. Below 72 kV, most often than not, they utilize a vacuum as the insulation and interrupting medium. Okay, so above 72 kV, right, as you can see over here, I've indicated, it is much ideal, much economical, cost benefit, you know, and much safer to utilize SF6 as the insulation and also as the interrupting medium, right? Okay, so here it basically shows the types of GIS that we have. The first one is isolated phase bus capsulated switchgear. Okay, so basically you have individualized metal enclosed buses, right, that are separate from each other in an enclosure, right? Okay, so that's what the first one is, right? Okay, then integrated three-phase bus. Okay, so the integrated three-phase bus shows just one single enclosure, right? Phase A, phase B, phase C, right? Okay, in one single enclosure, right? Separated by basically the insulating medium, right? Okay, so if you have a SF6 gas as the insulating medium, you see that SF6 gas will be all over here, right? All over this enclosure, right? On the other hand, the single phase one will have individualized compartmentalized enclosures, right? Okay, so you have a SF6 gas in this area and another SF6 gas in this area. So this is phase A, phase B, and phase C. So this one is a okay, so next one is the hybrid gas insulated switchgear. Okay, so then hybrid basically it's a combination of the isolated phase bus and integrated three phase. Next is the compacted GIS, and we'll see pictures of these product lines. Next slide is basically a typical product line from of a GIS from an OEM, right? Okay, so as you can see over here, right? Okay, so the first one is a three-phase type of the GIS, and basically this is the model number of the GIS, right? And this is also another three-phase, and this is the model number, right? Three-phase enclosure. So three-phase enclosure means that okay, all three phases are in the same enclosure. They are not separated, right? Okay, so this one is a single phase, right? As you can see over here, we have phase A, phase B, phase C, right? Okay, as the buses, and this is the model number, right? Next is another single phase, and this is the model number, okay? And next is a hybrid GIS. So a hybrid is a combination of a single phase and a three phase. Next is the eco-friendly, right? Okay, so this is more of a alternative SF6 gas, right? Okay, so this one is SF6 free, right? Where basically they are utilizing nitrogen, carbon dioxide, and oxygen as basically the insulating medium. And basically within the interrupters, basically is utilizing a vacuum. Right? Okay, so next is this one is for three phase, and this next one is for a single phase. Okay, so next line basically talks about the voltage level, right? The rated voltage that these product lines can be achieved. So we have 145 kV, 170 kV, 245 kV, 345, 550 kV, and for the hybrid, it's 420 kV. And basically, the new product lines that is for the eco-friendly, basically they are, I think they've successfully been able to achieve this one. But I think that they are working on this one. This one is basically in progress to be commercialized. And I think by the year 2024 or 2025, it should be fully commercialized. Next is the rated power frequency voltage, right? Okay, so basically over voltage conditions that occur due to over voltage. This is the Western 275 kV for all these product lines, right? Okay, as you can see over here. Okay. So next is to be able to withstand lightning impulse surges. Okay, so as you look at the ones, the GIS that are going to be installed outdoors, right? Okay, definitely they are going to be prone to lightning impulse surges. So the insulation medium should be able to withstand this amount of voltage for lightning impulse surges. Right. Next is the nominal current, right? Okay, so that is the rated current for these switchgears. So the first one is 3,000 amps, next one is 4,000 amps, and next one is 5,600 amps. Next one is 5,600 amps. Then for short circuit capability, right? Okay, so we have 40 kA and 50 kA. So the 40 kA is the symmetrical, and the 50 kA is the asymmetrical current. Okay, for current. So as you know that the asymmetrical for current basically takes into play the X over R ratio due to the DC offset component. Okay, so 40 kA is the symmetrical for current, right? And 50 kA is the asymmetrical, and asymmetrical is due to the DC offset due to the X over R ratio, the time constant L over R, and a contribution from motors. Next is the temperature, right? Okay, so this is the Western, right? Okay, the variation from -30 to 55 degrees. Okay, so basically that is one of the considerations that you have to take a look at when you are implementing a gas-insulated switchgear. That is the average temperature and the maximum temperature of the area has to be basically obtained. Okay, then the size of the bay, basically these are the dimensions of the bay for the GIS. Next, let's talk about the application side of the GIS, right? Okay, so basically, if remember, I made mention that for a GIS, reliability is very important, right? Basically, you have to consider that as for very important and critical customers. So most utility companies, for very important and critical customers, basically they try as much as possible to utilize gas-insulated switchgears. And like I indicated, that this can be installed outdoors and it can be installed indoors. Okay. And next is basically for congested cities, right? Okay. So if you have a highly populated city, right, spacing becomes a premium. Okay, so you want a reduced footprint to be able to fit into the space that you've been given, right? Okay, so basically, GIS becomes an option for you to implement. Next is for polluted industrial city, and I made mention about that, right? If you have refineries and other industries that basically emit a lot of pollutants, right? Okay, like and also, you know, if you're close to the shore, right? Okay, so the shoreline, the shoreline, then basically salt becomes a problem, right? From the wind, and also dust and sand and oil elements basically are due to pollution, and that is when you have to think about basically implementing a gas insulated switchgear. Next is basically, you know, as you know that renewables basically have penetrated and basically are now part and parcel of the power system network and has been integrated to it. And later on, basically, you know, we are seeing renewables as being about 60 to 70% of all the power producing um, portfolios that needs to be integrated to the transmission network. As such, GIS becomes an option, especially, you know, for as you know, for offshore facilities, right? Okay, spacing, it's a premium on offshore substation platforms, right? Okay, because larger spacing means larger costs, right? And basically, the goal is basically to be able to fit into a smaller spacing to reduce the cost. So as such, you know, the lower footprint and the smaller footprint of the gas insulated switchgear becomes the best option for you to select. And also the reliability part and its ability to basically um, withstand the elements of the offshore area. Then again, for onshore location, similarly, you know, it has been basically the best choice to utilize it for an onshore substation. Next is basically a very visual comparison that you can um, see over here, comparing an air insulated substation, right, to a gas insulated switchgear, right? Okay, so basically, when you're talking about an air insulated substation, it's the whole substation, right? Okay, it's the whole substation. If you're talking about an air insulated switchgear, right? Okay, then this can be this one, right? Or a disconnect switch. Okay, so that is the individualized component, right? Okay, so as you can see over here, right, for an air insulated substation, look at the larger footprint that you have, right? Very big, you know, and basically talking about the cost and also reliability, right? It is prone to basically birds, you know, animal strikes, and etc. And pollutants, right? Okay, you have all the contaminants in the air basically resting on all these components, and especially the insulators, right? You have a porcelain and polymers, right? You have they are all exposed to the elements, you know. Comparably to the GIS, right? They are all in a metal enclosed enclosure, right? Okay, so all the insulation and the components, everything is inside these enclosures. As such, that you know, you basically have a lower footprint, and also you are utilizing SF6, right? SF6 has a higher dielectric capability compared to Earth. So that is why you have a larger spacing and larger footprint if you are utilizing air as the insulating medium. Now let's talk about the typical bus arrangement that you can have for the GIS, right? Okay, so you can, the first one is a single bus, right? Okay, so you can have basically a single bus scheme. Then you can have also, as part of the single bus, you can have a double bus with a tiebreaker in between that. Okay, so most often than not, the tiebreaker, they call it the bus coupler, right? Okay. Then you can have a breaker and half scheme, right? Okay, so what is a breaker and half scheme, right? Okay, you have a breaker here, you have another breaker here, and you have another breaker here. Okay, so basically what you are doing is they are sharing this metal breaker, right? Okay, so they do that, especially, you know, if you want to have a maintenance on any of these breakers. Then basically you utilize the metal breaker. So they call it a breaker in half scheme. Okay, so these this is called a bay, right? This is called a bay. So you can have bay 1, bay 2, and P3, right? Okay, similar arrangements. Okay, so that is what you see inside for a breaker and half skin. Then you can have a ring bus. Basically, the bus arrangement is arranged in the form of a ring, right? Okay, so it's more of a reliability thing. Okay, then a double bus and a double breaker, right? Okay, so a double bus and a double breaker, right here. So that's how it looks like. Okay, so these are the typical bus arrangement that you can have for a gas insulated switchgear. So it's the same thing that you can have, same bus arrangement that you can have for a conventional air insulated substation. Next, I made mention that in the early part of the slides that I did talk about, right? It's you can have a single phase arrangement and a three-phase arrangement, right? Okay, so for a single phase arrangement, this is how it looks like. As you can see over here, the individual phases are basically uh, different, right? Okay, and segregated from each other. Okay, so we have phase A, phase B, and phase C, right? Okay, and they are all grounded independently to each other, right? Okay, so this is what you see over here, right? Okay, phase A, phase B, and phase C, right? Each phase is in its own enclosure, right? With an SF6 insulating medium. So this is the conductor, right? Phase A conductor, phase B conductor, phase C conductor, right? And around that is SF6 gas that is being used as an insulating medium. On the other hand, you can have a three-phase arrangement where phase A, phase B, phase C is in a single enclosure, right? Okay, and filled with this inside this enclosure is the SF6 insulating medium, right? Okay, so that is what you see over here, right? Okay, you have basically the three phase, right? Right, in one single enclosure. Okay, so for the three phase enclosure, okay, the maximum you can achieve is 170 kV, 69 kV to 170 kV, because basically, then the spacing becomes also the probability of arcing taking place becomes basically very high. So that is why the voltage levels basically come up to 170 kV, right? Okay, it's because as you can see over here, right? Phase A is in close proximity with phase B. Phase B, C, look at the spacing, right? Look at the spacing, right? So basically, it means that as you go up to higher voltages, right, then the probability of an arcing becomes very high, right? Okay, and so that is why the voltage level application is limited at 170 kV. On the other hand, as you can see over here, for the single phase, right, each phase is in its own enclosure, right? Look at the spacing, the big spacing, right? And basically you have enclosure separating each phase. So that is why for the single phase, basically you can achieve up to 800 kV. And because it's a lot of basically components and also cost, right? That is why basically the voltages start from 30 kV all the way up to 800 kV. Next, let's talk about the external connections to a GIS. Okay, so for remember, I indicated that GIS basically can be integrated to a power transformer, right? As you can see over here, right? This is basically the connection to the GIS. You have the GIS located here, and you have the power transformer also located here, right? Okay, so this one is the enclosure, right? And usually you have the oil to SF bushing. Okay, so that bushing is a horizontal bushing that is located here, right? Horizontal mounted bushing. Okay, and on this side is oil, and on this side is SF6, right? So that is why they call it oil to SF6 bushing. Right? So that is what is separating the oil side to the SF6 as a dielectric medium or insulating medium. Similarly, you have a similar arrangement in this picture right over here. So basically, you have the power transformer right here, right? Okay, so this enclosure right? So you can have the SF6 to oil bushing in here. Most often than not, the oil to SF bushings are mounted horizontally, but maybe occasionally, based on the design, it can be mounted vertically. Okay, so basically you have the oil inside the transformer, then you have the SF6 enclosure here feeding. Basically, you have all the phases feeding basically the GIS. Next, it's basically another arrangement. Okay, so as you can see over here, this is a three-phase unit, right? Okay, so you have phase A, phase B, phase C in a single enclosure, right? Coming off from this transformer, right? Okay, so phase A goes in there, and basically you have um, the bars, right? Another bars in close proximity, or everything in a single enclosure. So that's why they call it a three-phase unit, right? They are all located in a single enclosure. Next is a single phase, right? Okay, so single phase basically is individualized, right? Each phase is in its own enclosure, right? Phase A is in own enclosure. Phase C, B, and C as well, okay? And basically they run along this length, basically the enclosure all the way up to the GIS interface, right? Okay, so this one is basically when it is integrated to the air side. Okay, so you can have a air to SF6 interchange. So you have bushings that basically support that. Okay, so as you can see over here, you have air to SF6 bushings over here. Okay, so this one is a typical three-phase arrangement from ABDs. This one is actually an ABD product and a very excellent product. And basically, as you can see over here, this one is the local control cabinet. Usually, it's LCC, right? Okay, so this is where the control of this GIS all take place, right? Okay, so inside this enclosure are the interface with other equipment. For instance, if basically the GIS is protecting the transformer, you have a wiring that is coming from the transformer that comes in here, and also the interface to the SCADA. If you have a DCS or a SCADA system, an annunciator system, basically the wiring comes from here to there. So basically this one is to control the GIS and also acts as the interface between the DCS or the SCADA system and also the field equipment. Then this part is where the VTs are located, right? The voltage transformers, instrument transformers are located. Okay, so this one is basically SF is gas density. If you are testing for the gas density, this is the port that you use. And if you want to fill, let's say you receive an alarm and you want to fill the GIS with the SF6, these are the ports that you utilize. Okay, so this one is just a single bay, right? Okay, so as I indicated, complete GIS lineup has a lot of multiple bays, right? Okay, so let's say this one is 1, 2, 3, 4, 5, 6, right? Okay, so you can have multiple bays that are basically tied together. Okay, so that itself tells you how easy it helps with installation, right? On these GIS modules. Over here is where the circuit breaker is located, right? Okay, so here is where the circuit breaker module is located. Now let's talk about the components of a gas insulated switchgear, right? Okay, so you have a circuit breaker, right? Okay, so you have a circuit breaker that helps to interrupt the fault if a fault should occur. You have a circuit breaker that is supposed to be close to energize the circuit that provide power to the feeder circuits that you want to provide power, right? Okay. Then next is the instrument transformers, right? You have a voltage transformer and a current transformer, and basically the voltage transformer and the current transformer basically are there to provide a metering status and also for protected relays, right? Okay, and also basically real-time monitoring of basically it spits out voltage parameters, and the current parameters if you have it integrated to a SCADA system or a DCS system, right? Okay, then you have disconnect switches. Okay, so disconnect switches basically should be located on each side of the breaker, right? Okay, so that itself, if you interrupt the breaker, basically you open the breaker, then basically you can open the disconnect switches and F it. Okay, so basically Fing it basically allows you to basically take all the capacitive charge and basically capacitive charging due to the insulation elements at it. Um, the capacitance are formed by the insulation elements that you take it to ground to prevent it from building up, hazardous voltages, right? Okay. Then you can have FM switches, like I made mention that once you open this disconnect switches, you have to F8 through an FM switches. And for certain designs of GIS, you can have a fast FM switch. And like I said, the goal is basically to be able to take this, especially if you have a very fast front basically surges. So the goal is to utilize these faster FM surges to take the surge to ground. Next is the bus bars, right? Okay, so like I indicated, for the bus bars, you can have a single phase arrangement, one phase in its own enclosure, right? Okay, phase A, phase B, phase C in its own enclosure. Or you can have all three phases in a single enclosure, right? Okay, but the caveat is basically the voltage limitation, right? Okay, for if all phases are in the same enclosure, I think the maximum you can go is 175 kV. But for a single phase arrangement where you have each phase in its own enclosure, then you can go from 230 kV all the way up to 800 kV. And actually, the research and basically they are pushing for up to 1100 kV for GIS. Next is a bus coupler. Okay, so a bus coupler basically is basically a tiebreaker, right? Okay, so I think the industry name they gave it is so a bus coupler basically are two buses, and you have a tiebreaker that goes in between them. And so this is called a bus coupler. So it ties basically two buses together. Next is a lightning surge, okay, or surge arrestor. Okay, so as you know, um, if you have an overhead line, right? Okay, coming in. Okay, then you have a cable pot, right here. Okay, so the overhead line goes on top of the cable pot, right? Okay, so the cable pot is more of an apparatus bushing, right? Where basically your overhead line, phase A, phase B, phase C interface at the connection point in this cable pot, right? Okay, so then down there, it's basically where the feeder cable goes to your GIS. Okay. So what is done is at the interface, right? You basically there's something they call traveling wave, right? Okay. So basically this interface has a high impedance, right? There's an impedance change due to that. You have an overhead line, you have a feeder cable that is coming here. So what it does is basically at this point it's seen as a change in impedance as such that it requires a surge arrestor to be installed, right? To be able to withstand the high voltages due to the traveling wave. Okay, and inside the enclosure, depending on how far this and other substation arresters are from the GIS, inside the GIS, there might be additional surge arresters that will be needed based on the design. Next is the feeder cable, right? Okay, so this is an example of the feeder cable that is coming out from a component of the GIS and basically feeding the overhead and cable interface to feed basically your customers. Okay, so next we'll take a deep dive into other components, right? Okay, so basically like I indicated, this one is the local control cabinet, right? Okay, so this is where all your protection relays are located, right? Okay, and you have also your controls. Basically, you have your wiring to other field equipment like power transformers, etc. Then you have other communication and other wiring that is going to your SCADA system and your DCS system or real-time monitoring system, right? Then you or your actually sometimes it goes through the RTU, before it goes to your SCADA system, right? Okay, so then you have your disconnectors, right? Okay, so your disconnectors are basically isolators, right? Okay, so this is basically your circuit breaker, right? And so like I indicated, on each side of the circuit breaker are your disconnectors over here, disconnect switches. Okay, so you disconnect it and you ground the switch. So you have an earthing switch that is here. Okay, then you have a CT, right? Okay, so you have a current transformer, and its goal is basically to provide um, parameters, right? Okay, secondary parameters for mirroring and also for protective relay. Then you have a voltage transformer that is located over here. Similarly, it provides parameters for mirroring and also for protective relay. Then this side is the cable sealing end, right? Okay, so this is the feeder, right? So the cables are, three cables are for one for each phase are basically integrated here. So this is where the feeder going out basically comes from. Okay, so now let's take a much deeper dive into a typical cut section of a VT. Okay, so as you can see over here, for a voltage transformer, this is the terminal box, right? Okay, so this is the secondary wiring for the secondary side of the transformer. So if you have, let's say, a 69 volts line to neutral voltage, that's where the wiring is going to be located. Or if you have a 120 or 115 volts line to line voltage that you need for your mirroring and your protective relay, this is where you basically wire your signals for. Next is the core. So this is a typical core for the VTs, right? Okay, so like every instrument transformer, CTVT, they all have a core, right? Okay, so this one is basically the high voltage section, right? Okay, so this is where basically the high voltage side comes in, and if you have a 115 kV, 230 kV, 345 kV, bus, right? Okay, so it comes in here, right? Okay, then on this side basically are the wiring, right? Okay, so you have the primary conductor, and basically you have the secondary wiring. So the secondary wiring basically comes from here, right? And basically the other wiring from here to the terminal box. Next, it's a cut or a section of another important internal component. This one is the breaker, right? Okay, inside the GIS. Okay, so for the breaker, you have a stationary contacts, right? So this is basically the mechanism, right? Okay, so this one is the mechanism, and we have different mechanisms for different manufacturers, right? Okay, so for the breaker, we have a movable part and we have a stationary part, right? Okay, and we have an arcing contact, right? Okay, so the arcing contact basically is there basically to take the arcing that basically results due to the parting of the contacts, basically to take the arc out of the breaker. Next is the feeder cables, right? Okay, like I made mention that you have a cable compartment basically where basically the feeder cables are installed, right? Okay, so phase A, phase B, phase C are installed in here. Okay, and basically some of the manufacturers have made it easier for installation. That is, they have connectors, right? Plug and play, where basically you don't have to do a lot of basically work on basically terminating basically the cable. So basically you can easily basically plug it in and basically install it. Next is another section of how a feeder cable is installed. Name another picture of how another feeder cable is installed. Next, let's talk about the benefits of an overhaul. Okay, overhaul is an industry terminology for a major outage. Okay, so you have an overhaul or major outage. Okay, so outage we have a minor and major outage, right? Okay, it's all for uh, basically to support your maintenance strategy that you have in implemented. Okay, so one of the benefits, the first one we want to talk about is you perform or implement an overhaul or major maintenance, basically to prevent failures, right? Okay, so um, based on let's say real-time monitoring you have in place, let's say you've identified an SF6 leak, right? Okay, so you implement a maintenance to basically repair that SF6 leak, because what it is basically you are trying to prevent a failure of the GIS, because at a certain cutout gas pressure, right? Okay, your breakers are not going to operate, right? Okay, so that is what you are preventing. Then you want to extend the life cycle of the GIS, right? Okay, once you implement the required maintenance, as per the OEM, every GIS manufacturer basically specifies, delineates its required maintenance and inspections, that testing that has to be done on its GIS. So very, very important that you pay attention to the recommended maintenance that is required by the OEM of your GIS. Next is basically reducing the failure risk. And basically, as you implement the maintenance, what you are doing is preventing an in-service failure of the GIS. Especially, typical example is PD activity, due to the SF6 gas, right? If you have that, then basically your GIS is bound for failure, and that is what. So when you test the GIS and basically find a PD activity, then that is when you can utilize localization means to identify where the PD activity is, and basically implement the corrective maintenance that is required to extend and maximize the performance of the GIS. Okay. Next is basically validating the performance of the circuit breaker, right, or about the GIS, right? Basically by performing contact resistance, right? Okay, contact resistance testing is done, and also the travel velocity of the contact, right? Velocity of the contacts is also all motion uh, testing. Then also the mechanism, right? You perform inspection overhaul of the mechanism, and also the motion movement of the mechanism is also done. You do all this basically to validate uh, the performance of the circuit breaker, right? Because the circuit breaker should be able to close within a certain amount of cycle, right? And it should be able to interrupt fault within certain cycles. So when you do the testing, timing testing, contact resistance testing, travel velocity motion testing, and basically the motion testing of the mechanism, that is what you are trying to achieve, is to validate the performance of the circuit breaker. Okay, so next is basically to talk about the problem or the task that I need to handle, and basically this ties us into the actual title of this presentation. That is implementing a strategy or implementing an overhaul that needs to be performed on a gas insulated switchgear. Right. Okay, so as you know, if you install, if any OEM installs a gas insulated switchgear, right, what is it going to do? Is basically going to tell you the timeline that you need to perform a major overhaul, right? Okay, and this one they gave us 10 to 12 years. Okay, so this is what is basically utilized to identify or indicate your maintenance triggers for overhaul to be performed. And this time, inside the asset management software, 10 to 12 years basically was selected. So usually like a year or 6 months before the due date, it sends you a workflow for you to know that you have a major overhaul that will be due for this asset in any asset management software. Okay, and this total quantity of our GIS were about 10, and also they were mostly ABB GIS. Okay, so what is my goal? As maintenance engineers, my goal is to come up with a strategy to evaluate whether there's the need to implement this overhaul or major outage and the scope of work that is to be done for inspection, maintenance, and testing. Now let's talk about basically the risk, right? Okay, so first let's talk about the maintenance piece, right? Okay, so there's that maintenance and operation cost that you have to incur, right? Then also the power interruption that you have to achieve in each bay. Because if you have to perform a major overhaul, right, it will require power interruption. That means that basically you're going to take power feed to your critical customer. If you have a critical customer side, then basically they will lose power, have a power interruption. Then also there's that possibility of causing further damage, right? Okay, because you are intruding into the enclosure, and when you are intruding into the enclosure, if you don't have the right skills, or if even the one that has the right skills makes the least mistake, it's going to cause further damage. Next one is basically you are interrupting power to a critical customer, and basically you're going to have a loss of revenue. Next, let's talk about my actions. What did I do? Right? Okay, I have a strategy, and my strategy is to come up with the best recommendation, right? Either to implement a major overhaul or extend it, right? Okay, and that itself requires a lot of analysis, data collections, right? Okay, so let's walk through what my actions, what I did. So very, very important. And this strategy that I implemented can be applied to any other substation equipment, So not necessarily that it basically pertains to a GIS. Any other substation equipment where basically high maintenance cost becomes a factor, and also taking an outage. You have critical customers that you have to think about, right? And that itself is not an option, right? Okay, so that is when you can basically utilize these strategies and actions that I took. So the first one I did was basically to request for quotation from the OEM, right? And to perform a major overhaul. And as part of the request, I basically had a Teams call, and I basically asked the OEM to basically put a scope together on all the maintenance and inspection tests that they are going to perform. And they also provided their costs, how much it's going to cost them to provide that services. Okay, so that's more of a services, and that itself is part of the recommendations that the OEM will delineate in its maintenance manual that you receive as part of the GIS after during installation and after startup. Okay, so I received the quotation from the OEM with the itemized cost and the list of tasks that needs to be performed. Okay, so that is where the deep analysis, thinking broadly, checking with the industry best practices, and as you know that a lot of the GIS, the latest technologies, basically a lot of them, are newer, and not much maintenance testing has been done on a lot of these GIs. So within the industry, there's very little information. You can get it. There's very little. Because a lot of them basically rely on the OEM to for advice. So next, what I did was basically to retrieve engineering drawings. Okay, so as per every substation assets, right? Okay, so this GIS has its one lines, right? Okay, so the one lines is indicating its location in the power system network, and basically the one lines is going to confirm its rating, right? Okay, continuous rating, frequency, and also short circuit rating. Okay, then the schematics, right? Okay, the schematics basically will tell you all the internal arrangements, or especially the local control cabinets, right? And it's all its interfaces, and all the protected relaying and all the interlocks. Very, very important, okay, for maintenance activity to be performed. Then the wiring side, okay, so that itself also tells you all the wiring. Then What you can also, what I did was obtain the factory acceptance testing results and also the site acceptance testing during after installation and startup of the GIS. Then also went ahead and beyond that, basically went ahead and obtained the maintenance manual on the GIS. Okay, so what is the maintenance manual gonna tell me, right? Okay, so it's gonna delineate all the required inspections and testing overhaul that has to be done on this GIS for the circuit breaker, for the disconnect switches, for the earth switches, for the faster earthing switches, right? It's gonna tell me, the what needs to be done after a certain number of operations, right? Okay, so the OEM is going to delineate. Let's say, okay, for a circuit breaker, right? If the circuit breaker has seen quite, let's say, 5 to 10 faults, right? Okay, closing faults, right? Okay, then after this number of operations, then you need to perform a major overhaul. Below that, maybe they might specify that then you need to perform a minor overhaul, right? Same applies to the disconnect switches, right? The number of operations, and you can obtain this information from the cyclometer of these components. And same applies to the earth switches. If you have a faster earth switches, so same applies to that. Next, I obtain the maintenance history records, right? Okay, so looking at this GIS, it has been in operation for about 10 to 12 years, so there's not much maintenance history that has been done. I would say that a lot of them were more of a visual inspections that are carried out by the operations staff. Basically, what they do is basically they obtain data on the cyclometer uh, readings for the GIS. So all the informations were basically more of a lot of, let me put it that way. Then next is you can obtain from operations any SF6 gas leak that have occurred, any alarm due to SF6 gas leak, right? Any SF6 fill history, right? Okay, because once you have a gas leak and you check and validate that it is really a gas leak, then basically you have to top it up with SF6. You add and basically you do that in collaboration with the OEM. Right? Okay, so basically, those are all the information that I obtained from operations. Next is the fault history, right? Okay, so remember I made mention that as part of the operation, the cyclometer operation of the breaker, right? You also have to take a look at how many faults has the circuit breaker seen, or how much faults, closing faults that has impinged on the circuit breaker. Because that itself decides on uh, the whether you need to perform a major overhaul or minor overhaul. Right? Okay, so I had to obtain the fault history from protection uh, relay unit. Basically, add it as part of my Excel sheet. Then I indicated the cyclometer, right? Cyclometer means how many. You have a counter really. Okay, that basically provides an indication of the number of times the circuit breaker has operated, right? Okay. Then the disconnect switch has operated and the earthing switch has operated. And if you have a fast earthing switch, you can also obtain its operation. Okay, so what I did was after I had obtained all these data, right, I put it in an Excel format in a much more of a visualization, very nice Excel format sheet. Then beyond that, what I did was I moved a step further, to discuss, have a discussion with the operations and maintenance staff, right? Basically to have a feel, those that have been around since the installation of these GIS, just to because you have an assigned operations and maintenance person for each area, right? So where this GIS are located, right, there is a dedicated operations and maintenance staff. So went ahead and basically had a discussion with them, obtain any other information that I haven't gotten yet from the database, because remember, all these other maintenance history, one lines, three lines are all part of the engineering and maintenance database. But other information I have to get it, on hand through, face to face, talking with this maintenance staff. Then what I did was also, extend that envelope a little bit. Went ahead and they talked to industry, you know, participants, on best practice. Global is out there, other, consultants, out there, and just to see, how to feel about, what, you know, basically setting analysis and setting tasks that are basically, and also setting decisions that I'm gonna make, whether it makes sense or not. So very important that a lot of these things you touch base, because the GIS is a very complex switchgear, and especially setting decisions, you always want to touch base with industry consultants or industry best practices, because and also the other caveat is basically you're trying to save cost, because I mean, total of 10 GIS, right? If we have to go with exactly what the OEM says, right, by you know performing, and definitely we will stagger, this major maintenance or overhaul, right? You're talking about quite over $1 million, right, in maintenance and operation costs, right? Not to talk about the loss of revenue, by taking customers out on those feeders, right? Okay, and the inconvenience as well, right? Okay, so these are some of the things that when dollars, and especially millions of dollars comes into play, then you have to reach out to the industry and have discussions with the industry consultants, right? Okay, so now let's talk about the scope of work that I received from the OEM, right? Okay, so for the circuit breaker, just to mention a few, basically, performing circuit breaker timing test, and also testing of the current and voltages that is utilized by the close entry call of the circuit breaker. Then motion and velocity analysis to be performed on the breaker, contacts. Then also the breaker mechanism, right? And also the motor current and contact resistance, and let's say, and also in addition to that, there's an overall contact resistance that is performed for the whole circuit of the GIS. Then inspection and overhaul of the breaker mechanism. That's very important, because the mechanical breaker mechanism is basically what operates the breaker. So that itself requires an inspection and overhaul based on the cyclometer reading. Now let's talk about the disconnect switches, right? We have the phase and the earth switches. Okay, so this is what is the motor current and the contact resistance, and other inspections is done to make sure that the mechanical mechanism, everything is aligned properly for the disconnect switches. Next is the current transformers, right? Okay, testing is done, turns ratio, and basically magnetization, the saturation curve, and insulation resistance testing is also done. Next is SF6, and SF6 usually the partial PD activity testing is done, and that testing is very, very costly, about $80,000 for each GIS. Okay, so think about it. That's a lot of dollars, right? Okay, so that is why it requires strategy, and typical analysis and critical thinking. Next, let's talk about the analysis, right? Okay, so after I've received the quotation, right, I've put it in an Excel format, right? Okay, and also all the data that I've gathered, right, I've also put it in an Excel format. Okay, so what I did is basically comparison, right? Okay, so from the operations and maintenance, right, this is what I had, in my Excel sheet, right? Okay, and I compared it with what the requirement from the OEM, right? Okay, so what I found was basically, I'll say, all 10 GIS had minimal, right, cyclometer reading, right? Okay, if the OEM is requiring, like, let's say 5,000 operations, right, for the circuit breaker operation, for the disconnect switches, for the fast earthing switches, let's say about 1,000 operations, right? And closing fault that is going to be accounted by the circuit breaker and the operating mechanism. Let's say about 10 to 20, right? After I performed all my analysis, I found that only a couple of them of the GIS experienced only two closing faults, and even then, the cyclometer reading was reading less than 100, right? So compare 100 to 5,000, right? And the earthen switches, was even uh, lower than that. Okay. So I'm way below the OEM requirement, right? I have a 100 cyclometer reading, and the OEM is telling me that after 5,000 cyclometer reading for the circuit breaker and the disconnect switches and the fast earthen switches, about 1,000, I'm supposed to perform a major overhaul, right? So that itself tells me that I can postpone this major overhaul and save some dollars, millions of dollars, right? Okay, so that is itself, that is what they call a strategic analysis, right? Then one of the big things that basically it's a worry for GIS is PD activity, right? And PD activities comes from the SF6 installation, right? Okay, so that is one of the things that I have to worry about. So what I did was basically, take a deep dive into the SF6 leak history, right? Okay, so when I obtain the SF6 leak history, the data shows that none of the GIS has experienced any SF6 leak since its operation, right? So that itself is a great advantage, and basically gives me the indication that why do I need to spend that amount of money, $8,000 per each GIS here to perform a PD testing on the GIS, each GIS, right? Okay, so what I did was basically, indicated that we don't need a GIS PD testing. We can postpone the testing of the PD from the 10-year interval to the 15-year interval. And alongside that, basically, we can ask for quotation for installation of a PD monitoring device. Okay, so like I indicated, after the analysis, right? After the analysis, one of my recommendation is to extend the testing of PD from the 10-year interval, major overhaul interval, to the 15th year, right? So I can save only for the PD testing, I can save a total of $180,000, right? Then alongside the other option I did was basically have the OEM give me a quotation to install a PD monitoring device towards year 50, right? And that itself requires evaluation of need, benefits, and cost as well. Usually when these quotations are coming from the OEM, it is really pricey, right? Okay, so that itself, like I said, if there's the need, and I'm pretty much sure it's not going to be for all GIS, we have to basically come up with a GIS that has a lot of, let's say if we have a SFS leak, starting on any of the GIS from year 10 up to year 15, then that is when we need to consider it. Then also, if you have a GIS that is located in a very polluted environment. So one of the key data, and basically, I have to obtain it from, the meteorological um, unit. Is the location of this GIS and basically the pollution around that area, because the pollution itself will be a key factor in performing PD testing on this GIS. So after making that decision, you know, then the next thing I did was basically to have a conversation with the OEM, so basically, discussed, send, my recommendation, put everything in a nice table format and send it to the OEM, because whatever, because you see, this is like I indicated, the GIS is a critical gear. So if you're making such critical strategic decisions, you always want the blessing from the OEM. I mean, I do understand that sometimes, the OEM might basically argue, So what you can do is also, to basically, tie in an industry consultant, basically, request for uh, his, let's say 2 to 5 hours consulting, and fee and pay the industry consultant to basically be part of the discussion, right? And that itself also can help you. So you have somebody that is basically, also speaking for you to basically convince their OEM that there's the need to extend the major overhaul from a 10-year point to a 15-year. And in between that, let's say, 10 years to 15 years, still, you still have to basically have a strong monitoring in place. And let's say within the 10 years to 15 years, if you should experience any excess leak, then that is the time that you need to evaluate your recommendation and see if there's the need to perform any major overhaul on any of the GIS that will be experiencing any SF6 leak. The other option, the other recommendation is, and a lot of times, the OEMs, don't want that. It's basically for the OEM to train our maintenance personnel, right? Okay, so during, what I basically, like I said, I discussed with, other projects, right? So went to the project, department and basically found out that, there were about 2 or 3 newer projects for GIS installation, and it's the same manufacturer, right? Okay, so basically, I discussed with them and the opportunity to, tag along, have our maintenance personnel to be trained, basically, so that they can shadow this OEM technicians during the installation of and site acceptance testing of this GIS, right? And also, have them go for a formal training to be organized by the OEM on how to perform this maintenance during a major overhaul, right? Okay, because once our the GIS has been in operation for more than 10 years, right? So definitely the warranty is not in existence, right? Okay, so there's nothing like, if you have your maintenance personnel work on a GIS, then the warranty will be void, right? Okay, so we are past that stage, right? Okay, so that also became an option for us to basically push and basically have the OEM train our maintenance personnel. Okay, so definitely there will be that discussion that, okay, we can have your maintenance personnel do certain tasks, right? Okay, that is non-invasive tasks, and the ones that require very invasive and very skilled, then we can have the OEM do that during a major outage. So this option basically gives us the opportunity to be able to split the cost, right? Reduce the cost, right? Where we'll have the OEM perform, let's say, about 60% of the overhaul task, and our maintenance personnel also perform 40%. So we can save a lot of money in maintenance cost if there's the need within the 10 years to the 15 year for us to perform a major overhaul. So after that, then went back to change, basically the maintenance cycle, right, from a 10 to a 15 years in the asset management software. Right. So next, okay, so next slide. As you know that, as part of the global effort to basically reduce global warming, right? Okay, most utilities are driving, basically want SF6 free GIS. And modified, the state of California has given due date, like by the year 2025, there shouldn't be any switchgear that is going to utilize SF6 gas. They should push for alternative gas, right? Okay, so as such, many OEMs are basically pushing newer products and newer technologies out there that is SF6 free and utilizing basically carbon dioxide, oxygen, and nitrogen as the insulating gases. Okay. So the reason being that, like I said, that SF6 is a high contributor to global warming, right? Okay. So to mitigate that effect, that is why a lot of our utilities and states, countries are all pushing for the alternative gas that is SF6 free. Okay, so this is an example of what a manufacturer that is ABB has put out there as an alternative gas gear, and basically it's utilizing carbon dioxide and oxygen. And as you can see, as of now, they've been able to achieve 145 kV, right? Voltage, right? Okay, so this is a three-phase enclosure, right? And basically with all phases, phase A, phase B, phase C in the same enclosure. Okay, so next is for up to 420 kV, right? Okay, so for up to 420 kV, I think this is what they are working on to push, and also I think they have the capability and the ability to basically upgrade from existing SF6 to SF6 free alternative gas. So this is a typical example of what they have done, where an existing GIS was SF6, and basically they upgraded it to SF6 free gas, utilizing nitrogen, carbon dioxide, and oxygen as the background insulating gas. Then also they have something they call a hybrid, right? Okay, so there are another product that is out there is a hybrid, right? Okay, so for the hybrid, right, what they are doing is only the interrupting chamber of the GIS is utilizing SF6. So basically you have a high reduction in SF6, right? Okay, about 7% reduction in SF6 use. Right? Only the breaker compartment, the interrupting chamber, is utilizing SF6. All other passive components, right? Instrument transformer CT, VTs, cable feeder compartment. All other components are utilizing carbon dioxide, nitrogen, and oxygen as SF6 free gas. With that, that comes to the end of another very interesting topic. Take a look at it if you like it, and select the like button in YouTube, and hit the subscribe button in YouTube. And look forward to another interesting topic that is going to come soon. Thank you so much.